Let's come to the next presentation of the intro session. And I'm really happy to have with us Gernot Oreski, who's the division manager of the Polymer Competence Center in Leoben, Austria. In his role at the center, Gernot heads the smart material and surface testing. Division. He's an expert in polymers for photovoltaics, and his main area of research has been the aging behavior and long-term reliability of polymeric materials and components for demanding applications such as PV modules. He has a PhD in polymer engineering and science from the Montana University Leoben and serves also as a lecturer in the Department of Polymer Science and Engineering at that university. We're happy to have Gernot with us. Gernot, the floor is yours.
So I don't know, can you see my screen?
Yes.
In presentation style, right? Because I don't see it.
It's not in presentation style. I think you have to.
Okay, now it's in presentation mode.
Yes.
Okay. Thanks for the kind introduction, Michael. So my name is Gernot Oreski, and I'm working in PV since like 2003. So I guess I've seen something in these years. And today I want to tell you a little bit about my experiences, about the research we did in our institute, and what, to my opinion, you should look at when choosing packaging materials for long-lasting modules. So let's go back in 2003. As I said, back then I started as a young diploma student, tapping into the PV market. I did actually my diploma thesis in cooperation with back then Isovolta, which was then an Austrian company which first introduced the TPD backsheet on the market in the late 80s. Unfortunately, they went bankrupt 2 years ago. Nevertheless, 17 years ago, the market was quite different from now. So I looked up the numbers. I think the annual production was like 750 megawatt. That is now supposed a small fab and not the total world market. The total installed capacity was like below 3 gigawatt peak. That is also not a small fab, you know, from the big manufacturers. And let's say from the materials, the market was quite easy. So EVA was the absolutely dominating encapsulant. So there were no alternatives. Only for glass modules, PVB was used, but mostly for these security classes. Yeah, backsheet, the TPD backsheet, as we heard, was dominating. And back in 2003, as far as I remember, only few backsheet alternatives were available. So mostly polyester based from Japanese manufacturers. And also back then, some companies worked on the introduction of PVDF into the market. And there have only been, let's say, few companies providing backsheets, and PV backsheets for them was only a secondary business, and they were mostly dating in other markets dealing with laminates or coating companies, and for example, for electrically insulating materials, for example. The PV market right now, and I think we heard it in the presentation before, offers a broad variety of encapsulants and backsheets. So from fluoropolymer-based backsheets to a very big variety of fluoropolymer-free backsheets, but also in the last years in the encapsulant films, we saw different things happening. So from EVA, then all the developments of polyolefin encapsulants, thermoplastic or cross-linking. So we have a big variety here. What were the main driving factors? I would say it was always a reduction of the levelized cost of electricity. So more expensive materials have been replaced with more economic ones. So like the switch from Tedlar to non-fluoropolymers, or as we see now, the PET core layer to the polypropylene material. But of course, it was also decreasing LCOE means also increasing quality and reliability. So that was a second driving factor. And of course, you could add new features. For example, enhanced optical properties or selective permeability and so on. I will go to that later. So what are the failure scenarios of crystalline silicon PV modules? So this is taken from a report from the International Energy Photovoltaic Power Systems Program, Task 13, on performance, operation, reliability of PV systems. And it shows, let's say, typical failure curves, failure rates for PV modules. And we can actually differentiate between infant failures, which happens actually directly after installing modules. Then we have midlife failures, like PID, cell interconnect breakers, and so that happens after some years. And then we have the Verrad failure, which is mostly related to material degradation. So where does testing and R&D come in? Actually, infant failures are in many cases caused by bad lamination properties, for example. Midlife failures, very often bad component selection. So some or most of these failures are actually avoidable, but you need to put a lot of effort in it. So have extensive R&D and also do extensive quality and reliability testing. And that is costly. Yeah, material degradation you cannot avoid. You can just delay it, especially when we talk about polymers. We can extend the lifetime with proper stabilization, but that's also a thing. Proper stabilization costs money. So it's always like the balance we have to find between effort, cost, and actually what we gain from these changes. To my opinion, in the future, because of this whole variety of materials coming up and getting importance in the market, in the future we will see much more failures related to compatibility issues. And I think a check of the compatibility of each PV module component will get more and more important. And what am I talking about when I say compatibility issues? I'm talking about adhesion of the single layers and the materials in the module. I talk about corrosion, and I talk about yellowing, especially backsheet yellowing. Because what's the matter with adhesion? On the one hand, adhesion is strongly dependent on lamination parameters, and it's coupled, for example, with the cross-linking. But when you reduce temperature or time in order to get faster and save money, maybe you get less adhesion than needed, and on the long term you get delamination. The other thing is adhesion, for example, between backsheet and EVA. Let's say back then when just TPT and EVA was there, it was easy. The backsheet manufacturers made some surface treatment of the inner layer, of the cell side layer, and guaranteed adhesion to EVA. However, with these whole new materials, you cannot just optimize it for EVA, because when you make a surface treatment optimized for EVA, that maybe does not work for a TPO backsheet or for a POE backsheet. So that's the first challenge. And also there are known material incompatibilities. For example, polypropylene and polyethylene don't like each other, so they don't mix, and it's actually quite troublesome to adhere them. And this can be seen, for example, there are already manufacturers of alternative polyolefin-based encapsulants out there. They ask, what kind of backsheet do you intend to use? Or they give this information. Okay, we tested our product with these types of backsheets, and here we approve, but please don't use it with this backsheet. So that's a thing that's happening. For corrosion, we see a broad variety of new ribbon materials, interconnection technologies, and encapsulants film coming up. And sooner or later, we will also, unfortunately, have our surprises there, I guess, in the best or in the worst case. Yeah, and why is backsheet yellowing an issue? In most cases, backsheet yellowing is some sort of migration and then reaction of additives coming from encapsulant and backsheet meeting at the interface and causing this yellowing reaction. And also here, a proper design matching could avoid this kind of degradation mechanism. So how to avoid this stuff? You should test. And you know, in polymer engineering, we often say we have this development or testing pyramid. And you see, we go for from the raw material, we make our components. In our case, it's the encapsulant and backsheet films. We are talking about laminates, mini modules, and modules. And you should do all of it in order to get high quality and highly reliable PV modules. And as the pyramid shape, you know, at the base of the pyramid, you actually test a lot of number of specimens, and you go to the next level just with the most promising materials. And in the end, you make just some module tests with the most promising candidates that have not been eliminated in each step. The thing is, the higher you go up in the pyramid, the higher is actually cost and effort of testing. So in the past, unfortunately, abbreviations have been taken. I will show a very bad example of this. Therefore, we say, let's say, unexpected PV module failure modes occurred after some years of deployment in the field. So who should do this testing? Actually, material testing, I think that's the duty of the material or film supplier, and usually module manufacturers don't touch that. But a module manufacturer should start with film testing and work its way up until full-size module testing in order to guarantee the lifetime. So let's go through the simple levels. So what can we learn from testing of polymer films? Okay, we learn something of principal chemical, physical, and mechanical properties, and we can learn something about the intrinsic degradation behavior of the polymers itself. So what are the advantages of testing on polymer film level? It's actually, you have an easy sample preparation and sample handling. You only need small aging chambers, and you have all characterization methods accessible. So we're talking about all destructive and non-destructive characterization methods you can imagine in polymer testing. What needs to be considered? Influence of sample preparation, for example. So you should, when you do some aging studies of your backsheet, please cut your specimen before you put it into a climate or a UV chamber. Because when you do that afterwards, you know, you just expose a film and then cut it after, and the material has already embrittled, you see these nice cracks are forming. And what you get is you get a biased result, and you get a false positive degradation behavior. That means degradation starts earlier just because of these cracks, which have a notch effect and for example, lead to further backsheet cracking in the end. So what do we miss when we just do testing of polymer films? We miss all kind of material interactions and compatibility issues. Actually, we miss the microclimate of a PV module, and we miss all the processing influence coming from lamination. So we don't see corrosion effects. We don't see yellowing effects, for example. So some examples of where testing of polymer films is actually quite useful. For example, when you do a thermal and thermomechanical characterization of the encapsulants. So what do you learn there? You see, okay, where are my melting temperatures? You see actually something about the cross-linking of the material. When you do thermomechanical properties testing, you can learn something about shear modulus and shear viscosity. So parameters that are important for a PV module lamination process. And actually, you can use this method in order to optimize your process to see, okay, actually, looking at these thermal properties, cross-linking starts around 120 degrees. So that's the temperature we need in the sample. From DMA, you see softening starts at 80 degrees Celsius. So you shouldn't apply the vacuum before that because then the material is much stiffer and you may introduce stresses. So this is quite handy and useful. Another thing is, for example, yeah, you can measure, for example, certain properties and use it for some further analysis, further modeling. And that's an example we presented this year at the PVSec. So we measured the coefficient of thermal expansion for different backsheets. And as most polymers, we have anisotropic properties there. And when we increase the temperature, sometimes we also have negative thermal expansion coefficients. That means shrinkage. And what the colleague from Fraunhofer ISE, Pascal Roma, did then use these values for finite element analysis and found out that, you know, because of these anisotropic properties, we have an increased probability of cell fracture during lamination. Okay, let's go to laminates. So we take a small piece of glass, put encapsulant backsheet, and sometimes other components like ribbons or pieces of cell in there. So what can we learn there? Yeah, we learned something about material interactions and compatibility issues, so like discoloration, corrosion, or adhesion. Advantages, as before, easy sample preparation, only small chambers are needed, and yeah, you have most characterization methods accessible, except when you need to do some standardized specimen for mechanical testing, that's a little bit challenging. What needs to be considered, even though we have like the encapsulant backsheet glass structure, the microclimate is still different from full or mini modules because we have different diffusion lengths for oxygen, water vapor, or in case you use EVA for acetic acid. Yeah, and the processing influences related to size or volume may be different. So what do we miss? Still a lot. We cannot measure power, so we may see discolorations or effects, but we don't know its impact on the power output or its relevance for PV module performance. And still we miss some very specific delaminations, for example, when we put in full cells and have this delamination above ribbons, as shown here. One example, what we did a few years ago, we tested actually are there some interactions between electrically conductive adhesives used for replacing the solders in ribbons with different type of encapsulants. So we just screen printed these 3 EKA types on glass, encapsulated them, put them in some weathering chambers, and what we found out, yeah, in most cases nothing is happening. We just saw a little bit of hardener migration from the ECA into the encapsulant, but we didn't see any correlation with power loss of the test module. And so our conclusion was actually, yeah, this lamination process and also the accelerated aging is not inducing any harmful interaction between ECA and the types of encapsulants we tested. So let's go to mini modules. What can we learn from them? Yeah, for the first time, we learned something about PV module performance because we can measure power output. What are the advantages compared to full-size modules especially? Yeah, we have a manageable sample preparation. So you need to prepare modules, but they're small, you can handle them, and you don't need the big chambers for testing it. So what needs to be considered? That was a mishap that happened to us. We didn't think of when you use, like, you know, for mini modules, often you don't use hardened glass for handling reasons, for price reasons, you just use standard glass. And then after some time, we found out, oops, we didn't check the UV cutoff. And so we tested like 5 different classes. And then we saw, okay, the UV cutoff is somewhere between 300 and 320 nanometers of UV wavelength. And that's actually the most damaging part for the polymers. And so when we use a very shielding glass for the mini modules and a non-shielding glass for the 6-cell modules, there will be, or the full-size modules, there will be a discrepancy in testing. Yeah, and when you want to have time series, you can only use non-destructive characterization methods with these modules. What do we miss? Influence of components like frame or junction box. We miss realistic mechanical behavior, so talking about stress distribution and deformation levels. And also, we tend to overestimate power losses because we still have shorter diffusion lengths for water vapor and oxygen, for example. So, and finally, full-size modules. What can we learn? Most of it, so impact of the observed material degradation modes on power output. What are the advantages? We see all processing related influence, the microclimate is right, and we have realistic deformations and mechanical stresses. What needs to be considered? Yeah, it's challenging handling the big modules, and you need the big testing chambers. So what do we miss? And now we go back to the beginning. When we just do full-size module testing, we don't know anything about the degradation behavior of single module materials and their influence on the degradation modes of the PV modules. So, and we don't know a lot about influencing factors related to the bill of materials. So what do I want to say is you need all these steps in order to do proper testing. So why is it important to understand what information we got from these different testing levels? Yeah. Let's give an example. Let's talk about co-extruded backsheet. I think it was told before. First one was introduced in 2010, a polyamide-based backsheet. After 10, some other varieties are evolved in the market. We have some advantages compared to laminated structures. So like a full back integration that the manufacturer can do easy material modifications by himself. We have less production step. We have therefore reduced processing induced material degradation. We don't expect delamination, and in most cases we have also an increased sustainability. And the polymers used, polyamide, polypropylene, polyethylene, are usually cheaper than fluoropolymers or the PET films. What is missing still, and I think we will hear something later on from Kaushik, from DuPont, the track record. So PVF has a track record of more than 40 years outdoors. That's a thing we still have to achieve for this kind of backsheets. And unfortunately, we have a very, very, very prominent failure mode with the polyamide backsheet. So in 2010, it was introduced. And actually, the major motivation was, there was a shortage on the PVF supply. And the strong demand could not be met with PVF. And so many companies looked for alternatives. I think PVDF was one of the winners after that as well. And Isovoltaic decided going for polyamide. In the next years, around 10 gigawatt was sold. And unfortunately, after 6 to 8 years in the field, nearly all modules showed cracks, either these longitudinal cracks along the bus bars or square cracks in the cell interspaces. So we did a thorough investigation on the whole degradation mechanism, how these cracks are formed. Just a short story, what's the starting point? For this polyamide 12, we have a very unusual physical aging process. As you can see on this strained break tensile test results, and already after very short time exposure to heat, we have a significant reduction of the ability of plastic deformation of the backsheet. So we have strained break values around 15, 17%. So that's very, very low. Then after some years, obviously we have material aging. So in all cases, we observed formation of microcracks at local stress concentrations. So that was found on every backsheet we investigated so far. In order to get these cracks in between the cells, there was that was happening only in combination with certain EVA types, where we saw strong photooxidation and cracking from the insides. But in generally, the crack initiation and crack propagation happened because of the daily and seasonal temperature changes in combination with the different thermal expansion coefficients of the PV materials. So keep in mind, polymers have a 10 times higher expansion coefficient than, for example, glass. And this hindered expansion causes thermomechanical stresses. And that is the driving factor for the crack propagation. So the interesting thing is these cracks have not been observed in the lab. Why? Because this crack formation is a two-step process. First, we need heat and UV to reduce the fracture toughness of this material. And then we need a continuously occurring mechanical and thermomechanical load that causes these internal stresses and then is actually the crack initiating force. This strain break reduction was observed back then. I remember talks with the guys, but the consequences were totally underestimated by everyone in the market, or at least everyone I talked to. So what was done? The problem, we did single stress testing. So they did proper testing, several thousand hours of damp heat and UV exposure of the film, but there no cracking was observed because there was no thermomechanical load on the sample. Then they did modules, but they put one module in damp heat, one module in UV, one module in thermal cycling. In any case, no cracks appeared because what was missed, what should have been done was some sort, put the module first in damp heat, then in UV, and then put some mechanical load on it, then the crack will appear. So you should do some sequential or combined stress cracking. That's a big thing that has changed in the recent years. The awareness that you need to do this test to replicate certain failure modes. And I think just to point out the most prominent initiatives. So one is from NREL in the US, Denver. They have this combined accelerated stress test. The other one is developed by DuPont, this MUST test, which is a sequential stress test. And both of them actually led or could reproduce the cracking of the backsheets. Not only the polyamide backsheets, but also, for example, PVDF backsheets, which is quite prominent. So, what about polypropylene? Can this happen to polypropylene as well? Let's take a look at the properties of polypropylene backsheets. So, as you see from the strain curves, it's quite different to a PET-based backsheet. So, we have lower stiffness and a higher flexibility. When we expose the film to some damp heat and irradiance, you see polypropylene is quite stable, whereas for the PET, we see very quick embrittlement. What are other properties? Yeah, they are quite wide, at least this material we had, so it had a much higher reflectance. And actually that led to an increase in power of let's say 6 cell modules from 1.5 to 2.5%. So it's quite a nice thing. Instead of the grid we heard before, also use a very wide backsheet and you will get some power gain. But in any case, we observed yellowing at the backsheet encapsulant interface. And that's what I said. Some additives are migrating in there, reacting and causing this bad color. So you should really do your design matching in order to work it. So in another project, we had these backsheets outdoors for 2 years in different locations in Europe. And except for some photo-oxidation on the surface, we didn't find anything. So there was no polymer degradation in the bulk that we saw. So, and actually other studies that have been presented at PVSec in the last years, for example, I think Fraunhofer investigated the Bischoff and Klein material. Renault, François Rumens, hello François, I saw you are online. They presented also both results on their polypropylene backsheets, and I think the conclusion is from all these studies the same. So far, we see an excellent stability of PP backsheet films, especially towards UV. So Renault did like 24,000 hours of UV exposure and didn't see any discoloration or of the encapsulant or embrittlement or corrosion. Fraunhofer just saw yellowing, but in dependence of which kind of stabilizers were used. So, and that's the only thing that was rewarded. So, and additionally, when we use it with EVA, and that's the big difference to polyamide, we have an excellent stability towards acetic acid. So we don't expect environmental stress cracking with this material. To summarize, I think we all know encapsulation materials, backsheet encapsulants play an important role in PV module reliability because most of the prominent PV module failure mechanisms are linked to the polymers used. The long-term stability is determined by which kind of material you choose and what kind of interaction they have. And when you do a proper design matching or check the compatibility, you may certainly reduce degradation rates or avoid certain degradation modes at all. And my speaker before mentioned PID, for example. But each material combination should be tested thoroughly before introduction into the market. So really do your testing, do your homework, and then you usually should get high quality modules. And all test levels from film to full cell modules are needed for a comprehensive understanding of the long-term material and module behavior. And most important, single stress tests are good and you can learn something from them, but very often they don't reveal certain degradation modes which are observed in the field. So we need combined or sequential stress testing in order to reveal these degradation modes. Overall, I can just say we need a better understanding of the module and material degradation modes. And this is a precondition for a successful development of new components in reliable PV module designs. Yeah, just some summary showing you, okay, which kind of advantages and disadvantages we have with the certain levels of testing. And with that, I thank you for your attention. And anybody who is interested in the presentation, just send me your email address in the chat. I can provide it with you. With that, I want to thank you for your attention. Thank you for the invitation, and I'm looking forward to questions.
Thanks, Gernot. So break-fix approach is not the right one in module manufacturing. Maybe one question, actually. You mentioned you spent quite some time of your presentation also on on the backsheets from isovoltaic, and
Yes.
polyamides market share is not so big these days. But what is the difference between today's products using that composition compared to the products that failed?
I'm not sure. Maybe it's a different polyamide, because polyamides exist in many different variations. So isovoltaic used the PA12 type back then. I didn't have the chance to look at these new developments. I think DSM and Tom Worth in the US, they have this. I just saw this year some results from NREL from this cast test, and they compared the old AAA backsheet with this with a new polyamide approach, and it failed, but after much longer time than the polyamide backsheet, the old one. So they certainly brought it to cracking, but I think 3 or 4 times longer times. So that's what I know about that.
Okay, thanks. I think we're running a little bit late. What I suggest, because I'm seeing that there's quite some discussion actually also going on in the chat, so feel free, everyone, to be interactive. So Gernot, maybe if there's any question, maybe you can even answer them in the chat, and people will be happy to receive that. So I would like to continue then. Thanks again once, Gernot, for your presentation, and
you're welcome.
I hope you have still time to stay with us a bit.
No, I stayed the whole time.
Wonderful, thanks.